today we're going to talk about the life cycle of stars. And stars go through a definite life cycle. They are born or created, and then they go through a series of different stages, and then they burn out and die. And one of the interesting things about stars, and will become more apparent as we talk more about the star life cycle, is they have different colors. And these different colors indicate different temperature stars, and they also indicate where the stars are in the star life cycle. The hotter a star is, the faster it's going to burn its life away. Okay, so you can see here in this picture, you can notice many stars of different colors. You see some whiter stars. You definitely see some redder, orange, and yellow stars, and you see some that are a little more of a bluer tint. So, how stars begin. Stars start their life cycle in what's called a stellar. Stellar is the word. Stellar means we're talking about stars. Nursery. So, the universe and space is filled with big clouds of dust and gas and particles. And this is where the stars are actually formed. So here are some pictures of some of these stellar nurseries, these big clouds of dust and particles. And once again, the clouds provide the gas and dust from which the stars form. Okay, not the kind of dust we're used to. Okay, these are grains of carbon and silicon. And carbon, of course, we know is a very simple atom, and it's the building blocks of all life. So there's lots of this carbon in the stars. And silicon, where we typically see silicon, is at the beach. Sand is made of silicon. So anyway, what happens is this dust, okay, and gas, because it has mass, it has gravity. And so it starts to attract more dust, and the dust pulls together and clumps together because of its gravitational attraction. And then it gets more mass, and that more mass pulls in more dust and more gas, and that gets yet more mass, which pulls in yet more dust and gas, and it pulls closer and closer together. And this contraction, or this pulling together, causes the temperature and pressure of this mass of big ball of gas and dust to slowly increase. And when this temperature and pressure increases enough, we get nuclear fusion. 15 million degrees Celsius, when the star gets to that temperature, nuclear fusion ignites or starts. Okay, so you're taking the hydrogen atoms and you're changing them or squishing them or combining them into helium atoms, and it also gives off energy, which just makes it hotter, and you get a chain reaction. And so we've actually got nuclear fusion. And the thing you'll note here by this equation is helium, or hydrogen, excuse me, these very light atoms with one electron and one proton are fusing together and causing helium, which is a heavier atom. So when we've got nuclear fusion going on, we've got smaller atoms combining together to create heavier atoms. And this is where all heavier atoms are made, inside of stars. Okay, when stars are old enough and they've got heavy enough atoms inside them, atoms like iron start to be made. So all the iron in the world, in the universe, is made inside stars. And it's interesting to think that you actually have iron in your blood, in your hemoglobin. That's what gives it its red color. It's what carries the oxygen and allows you to breathe. And every little atom of iron in your body was created inside a star. So anyway, the energy comes from this fusion reaction. The mass of the 4 hydrogen atoms is bigger than the mass of the helium atoms, so when they combine, some of that mass turns into energy. Our good friend Albert Einstein discussed this relationship between energy and mass, and that's what his famous equation, E energy equals mc squared, mass times the speed of light, which is a constant, squared. Okay, so anyway, you've got gravity pulling in, but you've got this energy being released and this heat being released that's pushing out. Okay, these two balance, and what is happening with the gravity pulling in and the heat pushing out actually determines the stages of a star's life cycle. When these change, it signifies the change in the star's life cycle. Okay, they're all different types of stars. There's our picture of our colored stars again. And once again, different colors of stars refer to different temperatures. So, remember how we look at stars. We look at stars through electromagnetic radiation or light. Okay, so we look through telescopes, and of course we know about the visible telescopes where we see light in these visible bands, but stars also give off light in the infrared, the UV, the X-ray. They give off all of these different wavelengths of light. The only ones we can see with the naked eye are the visible. So back to the different colors. Okay, usually we think red or orange is a real hot color, but this is a little opposite of what we typically think or what might be intuitive to us. Blue is actually the hottest. But if you think of a flame and think of what color blue or what color flames is the hottest, you'll know we usually think blue is the hottest flame. So now it makes a little more sense. Green is in between, is warm, and red is cool. And this is a great picture here because you can really see some green and some blue stars in it. And this is my favorite Hertzsprung-Russell diagram, so we're going to stop and talk about this one a little bit. You'll notice we have spectral classes, just how we categorize the stars. Luminosity, okay? Luminosity is how bright they are. Notice we rate everything by the sun, which is a 1 in luminosity. So up here, they're very bright. Up here, they're dimmer. You also know temperature, okay? 40,000 degrees to 3,000 degrees. That's a big range. This is super hot. This is super hot too, but it's not 40,000 degrees. So of course these new stars are very hot, and as they cool off, they get less bright and their temperature decreases. And then magnitude or size, how big these stars are. Okay, and most of the stars, 90% of stars, follow this sequence here, which we call Mace sequence. They start off with blue, they go into like turquoise, green, yellow, orange, red, and then they die. Okay, there's some massive stars that work outside of the sequence. It's a small percentage of stars, but we'll talk about that in a little bit. So, we get our stellar nursery. Okay. The materials collect, they become stars. Most of them, 90%, go through this life cycle like the sun that I showed on this graph here. So 90% of them do this. And when they start to burn out, okay, all of a sudden the energy is bigger than the gravitational attraction. They've lost a lot of their mass. They expand and become a red giant. When our sun does this, it'll actually fill up further into the solar system than where our Earth is. So it will actually burn out and destroy our Earth when that happens. That's the bad news. The good news is this is not going to happen for millions and millions of years. And then it basically like explodes and gives off all this material and becomes what we call a planetary nebula. It leaves a little cool white star in the middle that's a white dwarf that eventually burns out and becomes a black dwarf. Now there is some percentage of material in these stars, or some percentage of these stars that have masses much, much bigger than the sun, 1.5 to 3 times the mass of the sun. And these giant stars, then when they burn out, they become what we call these red supergiants, and then they explode into a supernova and become either a neutron star or a black hole. Once again, remember this is about 90% of stars. This is a smaller percentage that are big, massive stars. They become red supergiants, explode in a supernova, leaving a neutron star or a black hole in the middle. Neutron star is made out of neutrons, which are particles we find in atoms, neutrally charged. A black hole is the mass left of a star contracts, and it's so massive in such a small area that it just sucks in everything around it, including light. So, death of a star. Here we go again. When the fuel runs out, the core collapses. The outer regions of the star split outwards in a supernova. Okay, a supernova can shine more brightly than a whole galaxy in the sky. So we actually observe these with telescopes. We can see these stars exploding. And the interesting thing is the life cycle of a star lasts over millions and millions of years. But this event happens sometimes for a few hours or a days. So it's a very short event compared to the life cycle of a star. So there, the supernova explodes, leaving the neutron star. Okay. So stars like the sun, the helium's exhausted, the outer layers explode, and this is some pictures. They become nebula, and you can actually see little bitty stars left in the middle. They're really pretty. Okay, these are all from the Hubble telescope. And at the center of this nebula, this little bitty stars, is a white dwarf. Okay, it's about the size of the Earth, but it's very dense. It has the mass of the Earth, about a ton for a teaspoon of material. And once again, the inward force of gravity is balanced by the electrons left in it, pushing each other apart. Okay, the massive stars, okay, some of the bigger elements, magnesium and oxygen, occur in those, and then even heavier elements are formed and burned. So some of your heaviest elements come from these massive stars. Okay, they become really hot when all the helium that starts in there is used up. The core collapses, becomes massive, hotter, and that's when these bigger elements are made. Okay, so here's a picture of a massive star. This is what happens. Okay, a succession of elements. Okay, so the hydrogen fuses to helium, carbon, oxygen, neon, magnesium, silicon, and iron. Okay, and iron can't be fused further. Whoops. It uses energy, and we get our supernova, our big explosion. Okay, and after the supernova, we either have a neutron star, if the mass of the core is smaller than about 5 times the sun, and you get neutrons. This is about 10 kilometers across, about 6 or 7 miles across. So for a star, it's not very big. And if the core is very massive, if this is about a very massive star, about 5 times as big as the sun, then it just collapses onto itself because of the mass. And it's so massive in such a little space that it just sucks things in like light. Okay, so once again, we got the life cycle of stars here. Okay, this is the massive star cycle here. Okay, where we get these massive stars. They become these super red giants. They explode in these supernovas, and they become either these neutron stars or these black holes. I think that's a neutron star and that's the black hole. It's hard to tell. Anyway, we won't worry about that. Most stars go through this life cycle here that we showed in the graph, explode into a red giant. Remember, super red giant. And then they push off the material, and we get a white dwarf, which burns out to a black dwarf. Okay?